Welcome to sitza.com.
Photoelectric effect. What is photoelectric effect? The emission of electrons from the surface of a metal on the incidence of the electromagnetic radiations is called as the photoelectric effect. So basically this photoelectric effect is when you strike a particular metal surface with high energy radiations, the electrons from the surface of the metal are ejected there. And this emission, this ejection of these electrons from the surface of the metal on striking the electromagnetic radiations is called as photoelectric effect. So when you take a particular metal and you strike certain radiations on it, you will see that radiation, the electrons get ejected, and this process is called as photoelectric effect. Now, the photoelectric effect we cannot explain with the help of the classical, theory of electromagnetic radiations that was given by the Maxwell. Rather, the complete explanation is provided by the Planck's quantum theory. Only the Planck's quantum theory can explain this photoelectric effect. So let's understand the photoelectric effect. When we take a particular metal surface and you strike certain radiations on it, what we observe that the electrons absorb this energy and the electrons get ejected. So when we use a particular radiation to knock out the electrons, we find that if you increase the energy of these radiations, if you increase the frequency of these radiations, the electrons are ejected with a higher and higher velocity. And if we use a very, very low energy, electrons cannot be ejected. So basically for every metal, we need a radiation of a particular frequency that can actually knock out the electrons from the surface of a metal. Because electrons, we know in the metal, they are very tightly held by the nucleus. There is a strong attraction, and to overcome that attraction, we need the energy. So the radiation that we use over here, this radiation should have this photon should actually have a energy that can overcome this attractive forces. And the energy that we need here that can overcome the attractive forces, that force of attraction between the nucleus of an atom and the electron, that is called as a work function. So work function, or the threshold energy, is basically the energy that we need to knock out the electron from the surface of a metal. So when electron absorbs this amount of energy, the threshold energy, only then these electrons can be ejected. And if we use the radiation that has the energy, we use a photon, a quantum here, that has a energy more than what you require. So therefore the excess amount of the energy will go in the form of kinetic energy of this electron. So let's understand it more clearly. When we are striking a particular surface, a particular metal with the radiations, electrons get ejected. Basically the energy of this radiation over here that we use, the energy of the one quantum, a part of this energy is used to overcome the this attractive force. That means a part of this energy, part of this quantum, is used to overcome the attractive forces, and that energy is called as a threshold energy. So this is the energy of the one quantum that we use here, and a part of it is used to overcome the attractive forces. And once they once the you take the electron away from the nucleus, the rest of the energy of this quantum goes in the form of kinetic energy of this electron. So when you knock out this electron, it has some kinetic energy. And how much will be the kinetic energy? That will be the difference in the energy of this quantum and the work function, the threshold energy. Threshold energy, or we call it as a work function. Correct? Threshold energy, or it's also called as a work function. If we use a quantum that has energy, suppose less than this threshold energy, correct, we're using the energy, we're using a quantum that has a less than this. So that means photoelectric effect cannot be observed. Electrons cannot be ejected. Okay, we cannot eject electrons if the energy of this quantum over here is less than the work function, less than the threshold energy. We can only knock out this electron from this the metal when we use a quantum that has energy equal to the threshold energy or more than that. So there must be some minimum amount of energy in the quantum, which actually is called as a work function, right? Only then you can eject the electrons from the surface of a metal. So this is the suppose energy of the quantum, and let's suppose h nu naught. This is the work function. This is the threshold energy that this electron must absorb, and then it will be ejected. It will be emitted from the surface of the metal, and the rest of the amount of the energy that is there, that is present in this one quantum, that will go in the form of kinetic energy. So basically the energy of this one quantum over here that we use to strike the metal, that will be equal to the work function, which is h nu naught, the threshold energy that you need to overcome the attractive forces, and the rest part of the energy will go in the form of kinetic energy. And if you increase the energy of this quantum over here, then what will happen? The kinetic energy will also increase. And for example, if we use a radiation that has a energy equal to threshold energy only, right? We use a radiation here whose frequency is actually equal to nu naught only, then the kinetic energy will be zero. You can knock out the electron with the zero kinetic energy. And if you use the radiation over here, if we take this radiation, we use one quantum over here that has energy equal to threshold energy, it will knock out, but the kinetic energy will be zero. And if this is less, if we use the radiation here that has less than the threshold energy, right, whatever you require here to knock out this electron, if we use a radiation that has a less energy than this, and if we use the quantum over here, a quantum that has energy less than this threshold energy, then you cannot knock out the electron. Photoelectric effect cannot be observed if the quantum over here that we use for the radiation, if that quantum has an energy less than this threshold energy. So we need certain minimum energy in the radiation, in the quantum, so that it can knock out the electron. So photoelectric effect is observed only when the frequency of this radiation that we use here is more than or equal to the threshold frequency. Only then you can observe the photoelectric effect. We take here a radiation that has an energy more than the threshold energy. Photoelectric effect can be observed, but no photoelectric effect can be observed if the radiation that we use here, if this radiation has an energy less than this threshold energy. So we use here, for example, the quantum, the frequency of this quantum is less than this work function, right? If the radiation that we use here, the frequency of that quantum is less than nu naught, then no photoelectric effect can be observed. No matter even if we increase the intensity of the radiations here, even if we use the high intensity of the radiation, still photoelectric effect cannot be observed, because again here in this case the radiation that we use here, it has a frequency less than the work function, less than what you require here to remove the electrons. So you need a particular radiation that has energy either equal to the frequency actually of this radiation, it must be equal to, or it should be greater than the threshold frequency. Only then the electrons can be ejected. So that means when we use a radiation that has an energy more than threshold frequency. If we use a radiation that has a frequency more than this threshold frequency, electron can be ejected. So this is only possible when we use a radiation that has a frequency more than this threshold frequency. So minimum amount of energy should be there, and even if you have a very low intensity, still the electrons can be ejected. Correct? If we have a very low intensity, photoelectric effect is still observed. Why? Because here the one quantum of energy, it has a frequency more than the threshold frequency. And again, if we use a radiation here that has the frequency more than this threshold frequency, on increasing the intensity, the number of the electrons ejected will also increase. If we use a radiation here that has a frequency more than this threshold frequency, so more number of electrons will be ejected, because in this case we're using the quantum that has an energy more than this threshold energy. And again, the excess amount of energy that is there, the rest part of the energy in this quantum, that will go in the form of kinetic energy. So here we observed these 4 important things in this photoelectric effect. When we use a particular radiation and the radiation has a frequency less than this work function, then no photoelectric effect can be observed. Even if you increase the intensity, the electrons cannot be observed. The frequency of this radiation, frequency of this quantum, it must be more than this or equal to the threshold frequency. Energy of the one quantum will be equal to the threshold energy, which is h nu naught plus the kinetic energy of the electron. So the quantum that we use, it should be equal to the threshold energy or more than that. Only then photoelectric effect is observed. And over here, if I rearrange this equation, I can say the kinetic energy of the electron will be h nu minus h nu naught, or kinetic energy of the electron will be h nu minus nu naught, which is actually the difference in the frequencies. If the difference in the frequencies over here is 0, then the kinetic energy will be 0. And if you see here, the frequency of this quantum, if it is more than this threshold frequency, kinetic energy will be more, right? So that means if you increase the radiation, if you increase the frequency of this radiation here, if you increase the frequency of this quantum over here, the kinetic energy will also increase. Concept. Thanks for watching the video. Bye for now.